to control the rest. And also the cockpit displays will be run by this one. Of course, there's backups and safety mechanisms here. There's a sort of heartbeat which goes from one to the other, and if that heartbeat stops, then this computer can take control of the other functions of the other computer. They're also monitoring each other, and if one computer sees that the primary computer for that task is misbehaving, it can also override that computer. All of the computers send data to a central data collection point which is stored locally, and hopefully what they're hoping to be able to achieve, we don't know if it will be technically possible, is to actually stream all of the data from the car in real time over the internet. So in order to provide that participation from primarily school kids, but of course for everyone.
So they have cable running then?
No, that will be wireless. So if we look at the front wheel assembly, here we can talk about a few things. This is using, this is double wishbone suspension, I think. I'm not sure, I'm not a big fan of that. But the other important things you got in here are, we'll start with the wheels. For this project, they literally had to reinvent the wheel. There's never been a wheel that's gone 1,000 miles per hour. And the forces on the wheel will be about 50,000 G at the rim. So it's got to be incredibly strong. Initially they thought they were going to have to use titanium. More recent studies, they've found an aluminium alloy which they can use, which should be able to withstand the forces involved. The next problem is the brakes. It's a very heavy car. It'll probably be a bit less than 7,000 tonnes when they want to brake it at the end of the run. But the main problem is that the brakes also have to spin at 10,000 RPM. Now, ideally you'd use carbon brakes. They're by far the best weight brakes. They can absorb the most energy without distorting. But at about, they did tests, and at about 8,000 RPM they just blow up. They just can't handle the rotational forces. So they're going to have to use ventilated steel discs, not dissimilar to what you've got on your own car. And but they don't have to be that bad, because on the desert, of course, metal wheels on a soft desert, they've got almost no traction anyway, so they don't have to be able to brake very hard at the end. And most of the braking, as we'll see later, will be done aerodynamically. So, onto the cockpit. This is, of course, Andy Green's office. So, he wants to be safe. How's he going to do that? They're making a monocoque, just like Formula One cars, but quite a lot bigger. This is a CAD drawing of the mould, and here it is in reality about 2 months ago. This has now been machined down. I saw a photo of that in the presentation I saw yesterday when I visited the club, but that's not online yet. So they are going to machine this into the shape which they want, then create a mould, and then create the monocoque on the inside of that mould. This is the cockpit. A bit more complicated than your own car. You've got the main speed dial here, and inside of that the power of the jet and the rocket. Battery systems and brake systems and fuel levels here. This indicator here will actually show him where he is on the track. So he knows when he's going through the measured mile basically, and also that he knows when to activate the rocket, which is absolutely critical. As you saw in the this one, that's coming up, that video. Also, an indicator to show what the status of the air brakes is, and these are more pressures and temperatures. Lots of buttons on the control column as well. The two green ones are the parachutes, the blue one is the air brakes. There's an abort button and communications buttons. He's also got a brake pedal on the left and an accelerator on the right, which controls the jet engine. The rocket will be controlled by triggers on the control column.
No missiles?
No missiles, no missiles.
What does the abort button do?
It basically shuts everything down.
No eject.
Well, very good. This is why we don't have an ejector seat.
Why Bloodhound is not fitted with an ejector seat. Imagine the car is doing 1,000 miles an hour and there is an emergency and Andy is ejected. The instant he is ejected, he'll be subjected to a wind force probably in excess of 10 tons. That would be totally unsurvivable. An alternative that is sometimes suggested is to eject the driver in his cockpit so that he is in a sealed unit and protected from the air pressure. This could be done, but it would be very heavy indeed and very complex. This approach could have reliability problems because all of the systems that lead into the cockpit must be extremely reliable, but also instantly detachable in the event of an ejection. Another reason why ejection is not something you can rely on is when something goes wrong in the car, it will happen very quickly indeed, and it may well be impossible for a computer system to react quick enough. And if it tries to do so, it is much more likely to respond to a false alarm. And on the thrust project we had 3 false alarms, and if we had used an ejector seat, that would have been 3 occasions when we would have ejected Andy and quite possibly killed him. Our solution is to keep the car firmly on the ground and Andy retain whatever control he still has and to stop the engines. That way he can bring the car rapidly to a stop, and if during that period the car should break up, then he will be protected by the fact that he is in the same type of composite tub that you'll see in a Formula 1 car.
So, there's also a possibility of being fire. This is a suit which Andy will be wearing. Unlike the fire-resistant suits which are worn by pilots and by Formula 1 drivers, this is heavier, but it can withstand fire for more than 20 seconds. Not only Andy himself, but all of his oxygen supply and the hoses and stuff will all be covered in this material, so that if there is a fire in the cockpit, he will be able to slow down. It will take at least 20 seconds to slow down if he's at full speed, and then he'll be able to climb out of the cockpit. So, onto the midsection here. You'll be able to just see here we've got water tanks. These are to cool the Formula 1 engine, which we'll get onto in a minute. It would have been too complicated to figure out airflows and stuff for a normal radiator, so we're going to use ice water to cool the Formula 1 engine. Directly behind Andy is the oxidizer tank for the rocket, and then behind that is the Formula 1 engine, which will act as the pump to pump the oxidizer to the rocket. That's what it looks like. It's a Cosworth V8 from, I think, this engine which was actually racing on a number of Formula 1 cars in 2010. It's produces nearly 800 horsepower, but 2 people can pick it up. It's incredibly light. If you're wondering about the time and when will it survive, well, it's only going to run for about 15 minutes, 60 times. And it's also going to be just power on and then power off. So compared to what it has to do in a Formula 1 car, it's very simple. So the expectation is that they'll use one engine and one engine only during the life of the car. This is a view from the top of the engine, the Formula 1 engine bay. Here you see the oxidizer tank. That goes here into the pump, which is under here, which pumps it through this tube At 1200 psi, it moves nearly 500 litres at 1200 psi in 20 seconds. So that's why you need 800 horsepower. The Formula 1 engine, the air intake will be well, just there under the between the canopy and the jet intake. That will be very warm, warm air. So there's a cooler to cool it down, and then the exhaust will just be pushed out the bottom of the car. Behind that, this is the jet fuel tank. It's very critical, that cooling system, because if this oxidizer tank gets too warm, which I'll talk about in a minute when we talk about the jet, the hydrogen peroxide, which is the oxidizer, will decompose and basically it'll blow up. So very important that we keep that cool. This is a close-up of the gearbox and pump. The gearbox is necessary because we need both the Formula 1 engine to run at its optimal speed to produce the maximum power, and the pump needs to run at its optimum speed. The Formula 1 engine is 18,000 RPM, the pump is between 9 and 10,000 RPM. So we need a gearbox to do that, also a pump for the hydraulic system. The rear of the car is actually also in 3 sections. You've got the lower rear chassis, the upper rear chassis, and the rear wheel assembly. Also the air brakes are here. The lower rear chassis is nearly finished. This was the first part of the car which was started to be built last year in November, and it's very nearly finished. This is what it looked like about 2 months ago. This is upside down, so this is actually the underside of the car, and yeah. So hopefully in the next presentation I'll be able to show you the finished piece.
Who's building this?
This one's been built by Hampson Aerospace. They're all aerospace companies. The composite tub is being built by people who also build composite cars for Formula 1 and stuff. The upper chassis. Now, initially, they were going to have a cross-sectional structure under this tube structure, but aerospace companies are not used to building that sort of structure. It's the sort of structure which you might see in racing cars, open racing cars. So, in order to simplify that, and for their manufacturers, they went back to what is very common in aviation, which is a system of ribs with stringers along the length, and with the skin actually being a structural part of the aircraft. This system also makes it easier to attach the fin, actually. One of the problems though with that is that they were first assuming if they had a skin which didn't take structural load, they'd be able to just take off panels to access the jet engine. Now that the skin is going to be a structural part of this component, they won't be able to do that. They'll make hatches so they can access things which they need to access all the time. But if they need to do major service to the jet engine, they'll actually take this whole bit of the car off so that they can access the underside of the engine. Well, we'll go on to the engine before I go to the rest. Oh, first the air brakes, sorry. The air brakes will look a bit like this. 2 hydraulic cylinders, and well, when they're closed, this will be extended, and then it will retract to extend the air brakes. This is initial CFD testing of the brakes. They first tried a solid air brake, but that produced so much turbulence behind it that it would have ripped the rear wheels off. So they put some holes in it so that there's nearly as much drag, but the turbulence is not as violent. This is a pretty bad quality film, sorry about that, of how that air brake mechanism will work. So, onto the rear wheel assembly. This is looking now from on top. Of course, the rear wheel assembly is this area here. You can see where the rocket lies underneath. It's also a wishbone suspension And other notable part of this is the parachutes. 2 parachutes which attach here, and this plate is not only attached to the rear wheel frame, but actually by these poles it's connected to the upper chassis and the lower chassis directly. Because of course, when that pops open, if the parachutes are used, which is a good point because they probably will not be used, they'll be used an emergency system only if the air brakes fail. But if they are popped, there's going to be huge forces going through there. The jet engine. This is an EJ200 jet engine from a Eurofighter. Bloodhound Project has 3 of these. They were 3 of the 4 engines on the 2 prototype Typhoon jets. And that's why all of the instrumentation and stuff is on the underside. So on the Eurofighter, that's the easiest place to get it. For Bloodhound, that's problematic. For those of you who don't know how a jet engine works, this is actually a turbo fan. The core is the jet engine, and then at the front here you've got the fan. The fan blows air not only into the core but also around the core, very similar to what you see more visible on the commercial jets, of course. But in the military engine, this has the advantage of mixing cold air with the hot air, so you get a lower infrared signature from the engine. The air gets pushed in here, it goes through a compressor, pressed down, fuel gets added to it, it burns. The turbo bit is the turbine at the back here which drives the whole mechanism. And then, being a military engine, you can also throw extra fuel in at the back to give you even more thrust. Afterburner, commonly called afterburner. So, then on to the rocket. This is our rocket man. Daniel Dubb, he acts like he's just come out of the 1950s, typical 1950s Englishman. He's actually only 27. So he's having a bit of a hard time with it. The jet development of the jet is going much slower than was expected. This is a model of the jet engine. It's about 45 centimetres in diameter. It's not small. And this is what it looks like in the inside. This is actually a model of the 6-inch version. At the front of the engine, the oxidizer, hydrogen peroxide, comes in here and it hits a nickel or silver-coated nickel mesh, which acts as a catalyst. That, for those of you who are into chemistry, that produces this reaction. The decomposition of the hydrogen peroxide produces water and oxygen, which is of course what we want for the rocket. It also produces a lot of heat. And actually, just this reaction in this rocket will produce about 4,000 kilos of thrust. And in the first runs in the desert, when they go there, they will use just that reaction. There won't be any solid fuel. And they should be able to get up to 800 miles per hour with that, without the actual fuel of the rocket. The fuel of the rocket, you can see here, is in fins to increase the surface area so that more of it can burn more quickly. That will be used up in about 20 seconds. And then, of course, the reason why it has to come in at 1200 psi is because it has to be pushed out the back. This is a test rig which will be fired this week. Actually, they were going to fire this for the first time. They've had a lot of trouble combining the Formula 1 engine with the pump and everything, but they're there now. They're about to do the first real tests of it. Here you see the rocket, the Formula 1 engine and the oxidizer tank. This is a test, and this is at only 300 psi pressure. Here you see the water coming out and then it lights up. So turn the volume down for this one. So it's bloody loud. That, as I said, was only at 300 psi. So at 1200 psi, it will come out even faster. So there we have the car. So what will it look like? Something like this. Or this is a typical run, I should say.
Braking 1,000 miles per hour is a massive task in itself, but it's made even more difficult by having to achieve it in a limited amount of space. The hack skin pan has a very flat surface, but it's bounded by rocks. The space between the rocks is 12 miles long, and in the centre is our measured mile. This leaves us 5.5 miles either side to accelerate to 1,000 miles per hour and to slow down again. It's critical that Andy reaches the start of the mile at exactly the right speed. If he fires the rocket too early, it will burn out and he'll be slowing down through the measured mile. If he fires too late, he'll still be accelerating through it and may overshoot the track. For Andy to reach 1,000 miles per hour in just 51 seconds, he'll have to time the rocket firing perfectly. Here's what a graph of an ideal run would look like. The jet spools up and the 7-ton car starts rolling. 12 seconds later and the jet comes on to reheat. With the huge boost in power, the speed rapidly increases. 20 seconds in and we pass 200 miles per hour. Just after 30 seconds in and at 350 miles per hour, the rocket is fired. Again, the car lurches forward, subjecting Andy to a force of 2G. The additional air being forced into the jet enables it to create still more thrust. In just a few seconds, we pass through the speed records set by Campbell, Breedlove, Gavlich and Noble, as well as the sound barrier and Andy's own record. Bloodhound enters the start of the measured mile at 1,000 miles per hour. It reaches 1,050 miles per hour before the rocket burns out and the car stops accelerating. Having successfully passed through the mile, you'd think the difficult part was over, but it's actually just beginning. The air brakes are deployed. He's now losing 65 miles per hour every second. The parachutes can be released at 500 miles per hour. It helps to slow him still further, but the remaining desert is disappearing very quickly. Andy's foot hovers over the pedal for the disc brakes, but he can't use them until he's below 200 miles per hour, or they would shatter. At last, the wheel brakes can be used to bring the car to a standstill. The support crew will have less than an hour to ready the car for its return run, back towards the rocks at the other end.
So this is the official graph which from Ron Ayres, which there was a mistake in the video. He talked about 12 miles, actually it's only 10 because the 1 mile buffer at each end. Ron Ayres would fit in at ING because this is all done via an Excel spreadsheet where he simulates the run with 1/100th of a second at a time per row and produces this graph. This is the same as the graph which you just saw. One thing which would be better in that video is if they actually did it in real time. Then it would be really slow here, really slow, and then get really fast, and then go slow down and slow down and slow down. So that's shown in this graph, which is the same but in time. So you can see it takes him 30 seconds or so to reach 600, and then another 10 or 15 to reach 1,000, and then he's through in just 3 seconds, and then he has to slow down very, very rapidly in order to be able to stop before the end. Actually, at the end, you can see here it doesn't quite go down to 0. That's because they're going to actually drive the car around on the power of the jet engine. That saves them what they did with thrust SSC. They picked up the back of the car and they towed it and they turned it around. But they've decided to take the simple option now of just letting Andy turn it around. It's got, the steering is not very sensitive. It's normal car's got about 15 to 1 steering ratio. This car will have 30 to 1. So it's got about 120 metre turning circle. This is what a run should look like.
Bloodhound SSC, you're clear. Engine start. Bloodhound engine start. Ready to roll.
Also a mistake there, he puts his foot on the brake.
Yeah,
Don't worry about that.
So will Andy actually wait for the fuel to run out, or will he stop beforehand?
Theoretically, both will happen at the same time. To get the optimal acceleration, both will have to happen at the same time. That you start at a certain point and you use the maximum amount of fuel that it runs out just before you're through the measured mile.
Okay.
Yeah, but it is controllable. That's why they went for a hybrid rocket instead of a solid rocket, like a firecracker. Once you turn it on, you can't turn it off. So not a good idea in a manned vehicle. I don't know why they did it in the space shuttle. But a liquid rocket is more complex. You can see how complex it was just to organise a pump and stuff for the oxidizer. If you also have to do that for the fuel, it's twice as bad. And that's why they chose the hybrid rocket. It's for the cost indeed, and for the most simple, most effective rocket. So that's the end of the presentation, but not for you, because you should get involved as well. You can go to the website and join the 1K Club. You get emails and you get invites to things. If you're really enthusiastic like me, you'll fly there for the open days. You can also follow them on Twitter and Facebook. There's actually a lot of things on Facebook which they have not yet put on the website. Yeah, you can put your name on the fin. As you can see, there's a nice big fin which will now, because it's been enlarged, fit up to 120,000 names. At the moment they've got more than 12,000 names. It only costs £10. And your name can go 1,000 miles per hour as well. There's of course lots of merchandise and stuff, so you can give out as much money as you like on it. And yeah, I think it's fantastic, and I hope that you will too. Okay. That's it. Thanks.
Thank you.
Questions? Or do I have to disappear straight away?
Do they need more pilots?
Sorry?
Do they need more pilots?
No, there is specifically only one driver. They are not having a reserve driver. Because if you have a reserve driver, that question was asked at one of the meetings I attended. If you have a reserve driver, then you have to take care of that reserve driver. You have to train them up. You have to, make sure that they are just as well trained as a primary pilot. And this is a small project. Well, small. So far they've spent about £4 million there. So far they've spent about £7 million on developing the car to this point. And they'll probably have to spend £6 million next year and the year after that.
But they already have another pilot.
Yeah, well, that's why there's one pilot.
No, I mean the second pilot,
Andy,
the older one. What? Just putting your foot down.
No. That's why I showed the film of Thrust SSC. It happens incredibly quickly, and I would like to think I was trained as a pilot, and I would like to think that I would be able to do it. But seriously, I don't think so.
It happens the former record holder.
So quickly.
He's too old.
What is too old?
Yes, no, well, when Richard Noble, he broke the record, that was right at the limit of his ability. And that's physically. Why he, physically, mentally, that's why he went looking for another pilot.
Yeah.
Andy is trained as a mathematician. He's got a degree in mathematics. and he's very switched on. Of course, he was used to twin-engined vehicles, so that's why he got the job as a driver. And it's really the workload that you saw in that run. He said, "Dan, that was hard work." For him, it was hard work. So for a mere mortal as I, it's nearly impossible. And that was really exemplified when I went to see Thrust SSC at the Coventry Transport Museum. They've got a simulator which they show one of those runs in a simulator, and everything just happens so quickly you just can't keep track of it. Of course, you would get used to that with training, but still, it's a really tough job.
Like a special kind of Olympic.
Indeed. So, any other questions? That's it.
Okay, thank
you
you
very much for coming in.
Thank you.